Hi everyone, welcome to the fourth lecture on this third module where we are discussing principle of sensing. In this discussion, we have discussed three different transduction techniques. They are capacitive, resistive and inductive. We had a detailed discussion on resistive devices, that how change in resistance can be characterized, and based on that we can develop different sensors, particularly chemiresistive sensors for gas detection and some RH humidity sensors also we have seen. We have also seen some strain sensor, and we discussed that strain sensors are backbone of pressure sensors and force sensors. So in that discussion, let's take our lecture to another topic, which is piezoelectric. So piezoelectric transduction technique is very important for electroacoustic devices. So let us see what is piezoelectric effect, what are piezoelectric materials and how they can be used for in sensing applications. Okay. So piezoelectric effect is the generation of electric charge by crystalline material when it is subjected to some external mechanical stress. Okay. So please note that we are generating charge, and in certain cases if you have charge, polarized charges can generate a potential. So this charge that I am generating may lead to some voltage, we will see in this lecture. So this piezoelectric effect, which is basically the generation of electric charge by the crystalline material when it is subjected to external stress, this kind of phenomena is shown by some natural materials as well as some synthetic materials. Okay. So in natural material we have quartz as an example. Okay. And then we have synthesized material, or we call it artificially polarized materials like some ceramics, like barium titanate, okay, and some polymers like this PVDF. Okay. However, please note that in the existing form, PVDF is not a piezoelectric material. So you have to first pole it, then only it will act as a piezoelectric material. Okay. So piezoelectric materials also exhibit ferroelectric properties. Its name was derived by analogy with ferromagnetic properties only, though most of the piezoelectric material do not have iron. So usually this ferroelectric is confused with the iron materials or iron derived materials, but please note that these piezoelectric materials mostly or wholly do not contain any iron. Okay. So let us take an example of quartz, which is nothing but a silicon oxide. Let us see that how this compressive force or a tensile force can lead to polarization of charge in specific crystal, particularly in quartz. Okay. Say see this image where there is no charge generated at all, there is no polarization. Now when I am applying a compressive force, this shifts the atoms in crystal in this way. Okay. If you see this, positive charges are accumulating on the silicon side, okay, this side, while negative charges start accumulating in oxygen side. Okay. And this gives you a polarized quartz, okay, or polarized quartz molecule. Okay. Similarly, you can see it for this case. Okay. You have charges here and this side. So you have a positive and negative charges on this silicon oxide. So I can say that a piezoelectric effect is direction sensitive. So depending on what is the direction of the force applied, I may have this charges. Okay. So if earlier I was applying force like this, now I am applying like this. Okay. So the induced charges or the accumulated charges position changed. Okay. So now earlier it was here positive and this side negative, now it has just reversed. Okay. For example, a tensile force can produce a voltage of one polarity. However, a compressive force can produce altogether, just opposite voltage. Okay. However, to collect the charges, what you have to do is you have to make electrodes. This whatever I am talking is from a material. Okay. However, you have to probe these charges. Otherwise, how you will collect it or how you will sense this charge. Okay. So, to collect this electrical charge, a conductive electrode has to be applied on opposite side of a crystal. Okay. Something like this. So, these are your electrodes and this is your material, which is going to be, a force is going to be applied here, or this has to be pulled, okay, depending on its application. Okay. However, this thing is universal. You have to apply a electrode to collect this charge or to sense this charge. Okay. Therefore, a piezoelectric sensor basically becomes a capacitor. So, you have a piezoelectric material which is sandwiched between two conductors. Please note that these conductors are right now the electrodes which I have put to collect these charges, okay, or to trace this voltage. Okay. However, this piezoelectric material is actually sandwiched between these two electrodes. Okay. So, basically this piezoelectric sensor has become now a capacitor. Okay. So, I mean, what you need for a capacitor, you need a dielectric material in between the metal plates, and this dielectric material here is nothing but this piezoelectric crystalline material. Okay. This dielectric generates electric charge in turn of some applied forces or some applied stress. Okay. This will result a voltage across this capacitor. We will see what is the value of this capacitor after some time, or value of this voltage generated after some time, but right now let us have this qualitative description first. Okay. So, in crystalline dielectric, charge is generated at the location of the applied force. So, if I am applying my force here, the charge will be generated only at this point, or if I am applying over here, this charge will be generated only at this particular point. Okay. However, if I have this electrode, there are some electron in this electrode also. Okay. So, this metal electrodes equalizes the charge along the surface, or any imbalance in charge which is happening because of generation of this electric charge in turn of this force applied. Okay. So, it actually makes this capacitor not selectively sensitive. Okay. So, I may not know that where this charge has been generated. Okay. Because my electrode is actually compensating that charge. Okay. So, for that we have to make these electrodes in certain pattern, particularly if I know that on which positions this force is going to be applied or the pressure is going to be applied. Okay. So, the exact location of the acting force is possible to determine by measuring the response from selected electrode which is actually compensating that particular charge. Okay. Please note that this piezoelectric effect is a reversible physical phenomena. Applied voltage across the crystal can in turn produce mechanical strain. So, for piezoelectric effect, what we have seen is we have applied some mechanical stress and in turn I am getting some charge. Okay. Or this charge can be calculated in terms of voltage or potential difference. Okay. Now, I am telling that this piezoelectric effect is reversible phenomena, which means that when I applied certain voltage, okay, my crystal will be deformed, okay, or there will be some mechanical strain produced in the crystal. Okay. So, this is reverse piezoelectric effect. Okay. So, I have mentioned that applied voltage across the crystal can produce mechanical strain, but how it will be possible? It will be possible by placing several electrodes on the crystal. So, one pair of electrode delivers the voltage to the crystal and the other pair of electrode collect the charge resulting from the developed strain. Okay. So, you have piezoelectric as well as reverse piezoelectric in place if you have multiple electrodes. Okay. This method is used significantly in various piezoelectric transducers, and we will also discuss some piezoelectric transducers in this course. Okay. So, the simplified form of magnitude of a piezoelectric effect can be represented by polarization vector, particularly if you have xyz components of polarization, I can write the total polarization vector as pxx plus pyy plus pzz. Okay. So here x, y and z correspond to a standard orthogonal system aligned with the crystal axes of this piezoelectric system. Okay. So in terms of axial strain sigma, this polarization vector can also be written. So all this pxx, pyy and pzz can be written as pxx as d11 sigma xx plus d12 sigma xx and d13 sigma zz. Similarly, you can also write for pyy and pzz. Okay. Please note that in this expression dmn is the piezoelectric coefficient along the orthogonal axis crystal cut, and d is very important parameter for a piezoelectric material, and in some time we will see what is exactly d. Okay. So d coefficient we will again come back. Okay. But it is also known as piezoelectric coefficient, which is along the orthogonal axis of this crystal cut. Okay. And dimension of this d is basically coulomb per Newton or charge per unit force. Okay. So apart from this d, I have two more additional coefficients. In fact, there are three different coefficients. Let us define them first, and then we will see the mathematical relationship between them. Okay, we will try to establish mathematical relationship between them for better understanding, and we will also see what is its significance. Okay. Let us see, apart from this d coefficient, let us see what are other three additional coefficients. The first is g coefficient. Okay. So g coefficient is obtained from the division of corresponding dmn coefficient by absolute dielectric constant. Okay. So gmn is basically dmn by E naught into emn. Okay. So if you remember, a dielectric constant is nothing but absolute permittivity divided by permittivity of air, right. This is also known as epsilon r, right, or relative permittivity, right. So gmn is basically dmn by epsilon naught epsilon mn. Okay. Another coefficient is h coefficient, but let us see what is g coefficient in little detail and its dimension. Okay, because we have already seen the dimension of d coefficient is coulomb per Newton. Okay. G coefficient defines a voltage gradient or electric field produced by crystal per unit applied pressure. This pressure sometime for solid plates you can also think it as stress. Okay, because stress is also a force per unit area, but this is experienced by the material itself. That is why better to call it stress in place of pressure, but you can also correlate it with pressure. Okay. And dimension is volt per meter by volt per meter square. So you can calculate accordingly. Okay. Then another term is h coefficient. It is obtained by multiplying this g coefficient by respective Young modulus of the corresponding crystal axis. Okay. So you know that Young modulus for different axis along different axis for a material may be different. Okay, if you don't take a holistic approach. Okay, so h coefficient can be found very similar to g coefficient by multiplying this g coefficient with respective Young's modulus. Okay, so there is another coefficient which is coupling coefficient or Kmn. It determines the conversion efficiency of piezoelectric crystal. Okay. When I say conversion energy, you should understand that piezoelectric crystal actually it is a kind of converter only, similar to the we have seen definition for a transducer and a sensor. They are converter from non-electrical stimuli to electrical stimuli. Okay. Or if it is transducer, non-electrical to another non-electrical, right. So piezoelectric crystals converts mechanical energy to electrical energy, and for this coupling coefficient I am talking about this conversion only. So it determines the conversion efficiency of piezoelectric crystal, and if you take the under root of d and h multiplication, or d into h under root, is known as coupling coefficient. Okay. These terminologies may be useful when we will discuss the actual transducers, okay, or sensors. Okay. Let us see through one example that how this voltage is generated in case of a piezoelectric material or piezoelectric device. Okay. So, the magnitude and polarity of the induced surface charge are proportional to magnitude and direction of the applied force F. This we have seen with the example of a quartz, right. So, you have already seen that if I apply force in different directions, the polarity of the charge accumulated changes, also the magnitude changes depending on the force applied. Okay. And to quantify this charge, I have one equation where I will use d value, okay, with force. So, this charge q is actually equal to d into f, where d is the charge sensitivity of the crystal, or the d coefficient that you have just seen. Okay. I am not using d11 or d12 or d13, but similar to this you can also use these values, okay, depending on which direction or along which axis you are calculating the charge. Okay. But right now I am generalizing it. So, this charge is equal to d into f, where d is the charge sensitivity of the crystal, or the d coefficient that we have seen just now. Okay. For such a condition where this is your plate, these are two plates, okay, this is the force applied and T is the gap between them. Say W is the width and L is the length of this plates. Okay. So, this is your L and this is say W. Okay. And because of this force, there is a change in this thickness T as delta T. Okay. So, if I assume these things, I can write the Young's modulus as F into A divided by delta T by T. Okay. Because Young's modulus is nothing but stress by strain, and stress is here F by A and strain is delta T by T, right. I can write this. Same expression is written over here. If you simplify it, the Young's modulus comes out to be F into T divided by A into delta T, where A is the area of these plates, which is width W multiplied by its length L. Okay. This is the, so this is my Young's modulus. I am calling this equation as first and I am calling this equation as my second equation. Okay. Let us call the first equation where charge was equal to d into f. Okay. Now, let us put the value of f from the equation 2 that we have just seen. Okay. So, q will be equal to, so f here E was ft divided by A into delta t, right. So, from this if I calculate f, it comes out to be E A delta t by t. Okay. This is actually my force. Now, if I put this value in my first equation, okay, I will get d A into E into delta t divided by t, right. This is my charge. This charge is actually responsible for a potential V. Why? Because it is also acting as a capacitor. It is also acting as a parallel plate capacitor, and you know the charge induced on a capacitor is simply Q is equal to C into V, or V is equal to Q by C, where C is the capacitance between two plates. Now, I am calling this charge equation as equation 3, okay, and this is my equation 4. Okay. V is equal to Q by C. Capacitance is nothing but K into epsilon naught A by T. Okay. Now, I am calling this as equation 5. Let us put this value in the fourth equation, which is the voltage equation, V is equal to Q by C. If I put this and put this charge value from equation 3, okay, I will get Q, which is dAE delta T by T divided by this C, which is K epsilon naught A by T. If you simplify, this voltage comes out to be D into T into F by K into A, where K was my dielectric constant. Please do not get confused in dt and delta T. Delta T was the change in thickness, and here D is a separate quantity, which is my charge sensitivity. This D is my charge sensitivity and T is the thickness or gap between these plates, if I am considering this as a capacitor, but actually this gap represents the thickness of the piezoelectric material. Okay, I am calling this as equation 6. Okay, so this V is equal to D into T into F by K into A. Okay, I am calling this equation as equation 6. If I simplify this, I get V equal to dt by epsilon r into epsilon naught into F by A, because this value is coming from dielectric constant. Okay, we have just discussed the dielectric constant. Now, if you see this, F by A is the stress component, okay, or sometime you can also correlate it with pressure. Okay, so F by A is stress. I am calling it as S. Okay, so now I am calling this equation 7. Okay, now if I put the value of F by A in this equation of V, I get V equal to G into T into S. If I consider this G as D by epsilon r into epsilon naught. Okay, so if G is equal to D by epsilon r into epsilon naught, okay, I can write this as G into T into S. This V value can be written as this. I am calling this as equation 8. Okay, here G is the voltage sensitivity of the crystal. Okay, so now we understood that what is the significance of D and what is the significance of G. My D was charge sensitivity and G is my voltage sensitivity. Okay, and this voltage is equal to G into T into S. Okay, now if I find the value of G from this equation, equation 8, I can write that G is equal to V by T into S or V by T whole divided by S. Okay, V by T is nothing but electric field. I am calling it say E, okay, or electric field intensity. Okay, so G can be written as E by S or field intensity divided by stress. All right. So the charge sensitivity D is epsilon r E naught into G. Okay. For barium titanate, which is a ceramic, a poured ceramic or a synthetic ceramic, the voltage sensitivity is 12 into 10 power minus 3, and a natural piezoelectric material, which is quartz, is having several times high voltage sensitivity or G, which is 50 into 10 power minus 3. Typical permittivity value of these two materials are 12.5 into 10 power minus 9 for barium titanate, and for quartz it is 40.6 into 10 power minus 12 farad per meter. Okay. However, the difference is mainly in the charge sensitivity, which is 150 for barium titanate and very low like 2 for quartz. Okay. So in brief, we have seen that what is the charge sensitivity and voltage sensitivity of a piezoelectric material. We will be using these values or the definition of these parameters when we will discuss our sensors, particularly based on piezoelectric material. Okay. Now let us quickly see the mode of operation of a piezoelectric crystal. Okay. The piezoelectric crystal are used in several modes, and 4 important modes are thickness shear, phase shear, thickness expansion and transverse expansion. Okay. These are the modalities. Okay. The blue one denotes the thickness shear. Just see the force applied and the collection of charge or the potential dropped. Okay. The second is phase sheared. So, you are taking connection from one side and from one face, and force is applied like this. Then thickness expansion, this green one is thickness expansion, and then finally you have transverse expansion, something like this. So, the force is applied like this and charges are collected like this, or the voltage is dropped like this. Okay. So, these are the mode of operation of a piezoelectric crystal in different sensors or different transducers. Okay. Now, we have understood the piezoelectric properties. Okay. Let us summarize the important properties of a material or a desirable properties of a piezoelectric material which are suitable or which make it suitable for sensing application. Okay. First of all is its stability. Okay. Then high output sensitivity to external force, but should be stable with other parameters. When I say other parameters, means other external parameters, okay, like temperature, humidity and others. Okay. For these applications, quartz can be very suitable because it is kind of inert to these variations. However, even for larger stress, the output is very small for quartz. Okay. Then the alternate material is mostly in the form of barium titanate. Okay. It has advantage in the form of being polycrystalline, and we have seen that we may need depending on what application we are using it. Okay. We may need various size and shape of this piezoelectric material, and that is quite possible with the barium titanate. People have shown different shapes of piezoelectric transducers using barium titanate. Okay. Then another important characteristic the material should have is the low leakage. Okay. Then good frequency response is desirable for a piezoelectric crystal to be applicable in sensing application, and then finally a good voltage sensitivity. A good voltage sensitivity will ensure a better sensor fabrication, okay, or better device fabrication. Okay. So, with this we have understood the piezoelectric phenomena or piezoelectric principle of sensing. We will be giving some real example when we will discuss the force and pressure sensors. Particularly in those sections we will be using this piezoelectric material a lot. Okay. In the next class we will discuss pyroelectric material in detail. Thank you.